Inserting an element into our tree when it has no order is relatively easy. We'll just tack our node onto another node. Maybe it's a leaf, or maybe it's a parent with only one child. We only need to make sure that we're obeying the two children rule. We're given the root at the beginning, and we'll need to keep moving down the tree until we find an open spot. How long will it take to find an open spot? The worst case is that we travel down the longest path until we find the farthest leaf. In that case, we'll travel through the number of nodes equal to the height of the tree. But what is the height of a binary tree? Like we did with our sorting algorithms, let's look at some examples and reason through it. Here are two different trees. We can call these perfect trees since every node except the leaves on the last level has two children. It looks like this tree with 3 nodes has 2 levels, and this one has 7 nodes and 1, 2, 3 levels. As the tree grows bigger, each new level has the capacity to hold a number of nodes equivalent to a power of 2. Mull over that for a second. Each node can have 2 children, so each new level can have twice as many nodes as the one before it. Since we've gone back to talking about powers of 2, your mind should jump to log n. Does that apply here? Let's take a look. We see the same pattern that we saw in binary search. The number of levels increases near a power of 2. And now we have a good visualization to understand why. At every level, we're adding roughly twice as many elements. Every time we need to add a new level, or in a binary search, divide our array another time, it's because we're giving ourselves the space to allow for about twice as many elements. Remember that we're adding a power of 2 at each level, so when we count up the nodes overall, it won't be exactly a power of 2. Having 3 levels doesn't mean an overall node count of 8, but it does mean that the 4th level itself will have 8 elements in it.